Have you ever wondered why spider silk is so strong? The answer lies in its unique molecular makeup. Spider silk proteins, known as fibroins, exhibit a fascinating molecular composition. If we delve into the amino acid sequence, we find a meticulous arrangement, with glycine and alanine taking center stage. This isn't a random occurrence, but rather a carefully orchestrated symphony of biochemistry. The primary structure of these proteins is dominated by these two amino acids, resulting in a repetitive and modular sequence. This sequence is a hallmark of spider silk proteins, and it's not for show. It imparts unique properties to the material, providing it with the strength and flexibility that we marvel at. Consider it the underlying blueprint, the secret recipe that gives spider silk its extraordinary characteristics. This meticulous molecular arrangement is the foundation of the extraordinary properties of spider silk. How does a spider create this remarkable material? Well, the journey begins within the spider's own body, in specialized cells known as silk glands. These glands, found in the spider's abdomen, are the birthplace of silk, where an intricate dance of molecular processes unfolds. The synthesis of spider silk starts with the creation of silk proteins, also known as fibroins. These proteins carry the genetic information that dictates the exact sequence of amino acids that will compose the silk. This isn't a random process, but a meticulous assembly line of enzymatic reactions. Each amino acid is positioned with precision, in accordance with the genetic blueprint. But the process doesn't stop there. After the initial synthesis, these protein chains undergo a series of post-translational modifications. These are essentially finishing touches that further refine the structure of the silk proteins. They may involve the addition of chemical groups or subtle changes in the protein's shape. These modifications set the stage for the next act in the protein's journey: folding. This is where the proteins fold into a specific three-dimensional shape, a crucial step in the formation of functional silk. The folding process is guided by the unique sequence of amino acids in the protein, ensuring that each molecule assumes the correct form. This complex synthesis process results in the precise amino acid sequence that gives spider silk its unique properties. From the silk glands of a spider emerges a material that is both soft and stronger than steel, a testament to the marvels of nature's engineering. How does liquid become a solid, tough fiber? This is the question that brings us to the spinning process, the magical transformation that takes place within the spider's spinning apparatus. The spinning process begins when the spider decides to spin a web. The silk proteins, stored in a liquid crystalline state in the silk glands, are drawn into the spinning duct. Now, this isn't just any liquid. It's an organized ensemble of proteins, each meticulously arranged in a manner that sets the stage for the spinning process. As the liquid silk is drawn through the narrow spinning duct, an intriguing phenomenon takes place. The mechanical pulling aligns the protein chains, guiding them from a disordered liquid state to a structured solid form. Picture this as a chaotic crowd of people suddenly forming a neat, orderly line. This alignment is a crucial step in the transformation process. It prepares the proteins for the next stage, the formation of a solid fiber. But it's not just the alignment that's important. The silk proteins also undergo a change in their molecular organization. As they move through the spinning duct, they transition from an isotropic liquid state, where the proteins are oriented randomly, to an anisotropic solid state, where the proteins are all aligned in the same direction. This change in orientation is what gives the silk its strength and flexibility. The spinning process is a prime example of nature's ingenuity. It's a delicate dance of mechanics and molecular dynamics, a process that transforms a disorganized liquid into a structured solid. And all this happens in a tiny duct within a spider's body. This process is a marvel of nature, a testament to the complexity and sophistication of biological systems. It's an example of how even in the smallest of creatures there exists an intricate and finely tuned mechanism that allows them to survive and thrive in their environment. So the next time you see a spider web glistening in the morning sun, take a moment to appreciate the marvel that is spider silk. Remember that each strand was once a liquid, transformed into a solid fiber through a process that is as intricate as it is fascinating. This delicate interplay of mechanics and molecular dynamics results in the formation of the solid yet flexible spider silk. What gives spider silk its incredible strength? A question that has fascinated scientists for centuries. As we delve deeper into the mysteries of spider silk, we encounter the formation of beta sheet structures, a key player in the silk's remarkable strength. When the liquid silk is spun through the spider's spinning duct, the protein chains undergo a significant transformation. They transition from a disordered liquid state to a highly organized solid state. This transition is marked by the formation of beta sheet structures in the protein chains. Beta sheets are secondary structures in proteins, where individual protein strands align side by side, held together by hydrogen bonds. These structures are like the rungs of a ladder, providing stability and rigidity to the protein chains. In spider silk, the beta sheets are meticulously arranged and oriented, contributing significantly to its mechanical strength and overall structural integrity. These beta sheets form the hard, crystalline regions of the silk fiber, providing it with its impressive tensile strength. The formation of these beta sheets is not a random process. It's a carefully orchestrated dance, guided by the specific amino acid sequence of the silk proteins. The repetitive sequence of glycine and alanine residues in spider silk proteins is key to this beta sheet formation, creating a material that is both tough and flexible. So the next time you marvel at the strength of a spider's web, remember the tiny, intricate beta sheets that hold it all together. It is this arrangement of beta sheets that gives spider silk its unbelievable tensile strength. How can we apply the lessons of spider silk in our own creations? This question is at the heart of biomimetics, a field that seeks to imitate nature's designs and processes to solve human problems. Spider silk, with its extraordinary mechanical properties, is a prime candidate for such imitation. Imagine a material that combines remarkable tensile strength with elasticity. That's spider silk for you. It's stronger than steel and tougher than Kevlar, yet it can stretch to almost half its length without breaking. These properties are a result of the intricate molecular dance that happens within the silk. The interplay of intermolecular forces and molecular dynamics gives rise to a material that is both robust and flexible. Biomimetics aims to mimic these properties in synthetic materials, a challenge that has captivated researchers for decades. The goal is not just to replicate, but to understand the underlying principles that govern these properties. By doing so, we can create materials that are not only strong and flexible, but also sustainable and adaptable, much like the spider silk itself. The potential applications are vast, from construction materials that can withstand earthquakes to medical devices that can adapt to the human body. The possibilities are only limited by our imagination. Unraveling the secrets of spider silk could lead to a revolution in material design. With every strand we spin, we come closer to understanding nature's blueprint and using it to build a better world. Where could we use spider silk in our everyday lives, you may ask? Well, the potential applications of this extraordinary material are vast and varied. In the realm of medicine, spider silk's biocompatibility makes it an ideal candidate for sutures. These are the stitches that doctors use to close wounds. Unlike synthetic materials, which can cause inflammation or rejection, spider silk can seamlessly integrate with biological tissues. This can accelerate the healing process, reduce scarring, and minimize complications. Beyond medicine, spider silk's unique combination of strength and flexibility make it a sought-after material for lightweight textiles. Imagine wearing a shirt as light as a spider's web, yet strong enough to resist tearing. Or consider the potential of spider silk in the construction of bulletproof vests, parachutes, or even cables for suspension bridges. In the field of material engineering, spider silk holds the promise of advanced composites. These could be used in everything from aerospace components to sports equipment, offering unprecedented strength and flexibility. But harnessing the power of spider silk is not without its challenges. One of the biggest hurdles is replicating the intricate molecular processes of spider silk synthesis on an industrial scale. This involves not just mimicking the spider silk's chemical composition, but also the spider's unique spinning process. In the realm of synthetic biology, researchers are working tirelessly to engineer organisms or synthetic systems capable of producing spider silk. This could involve genetic modification of bacteria, yeast, or even plants to produce the silk proteins. However, achieving the precise molecular arrangement and mechanical alignment of the natural silk is a complex task. Producing spider silk at a scale suitable for industrial applications also poses significant challenges. Spider farming is not a feasible solution due to the spider's territorial and cannibalistic nature. Hence, researchers are focusing on biotechnological approaches to produce large quantities of spider silk without the need for actual spiders. Despite these challenges, the future of spider silk is promising. With advancements in synthetic biology and molecular engineering, we are getting closer to unlocking the full potential of this material. The road ahead is certainly filled with challenges, but overcoming these could unlock the potential of spider silk and transform numerous industries.